The International Space Station is the ultimate extreme home.
Space is an environment where human beings were not meant to live.
The most expensive structure humans have ever built. Here, in the most inhospitable environment known to man.
The only reason we can go there is by taking technology to provide us with everything that we need in order to stay alive.
With no air, food, or water, 250 miles above the Earth, it's an epic engineering challenge.
We as engineers are having to figure out how to make systems that provide all those functions that Earth provides in a tiny little can.
To reveal how the engineers pulled it off, we're going to take it apart and uncover what's going on inside. How the International Space Station and its superstructure secrets will help our species reach other planets and beyond. Costing up to an astonishing $150 billion. This is an unprecedented home.
The ISS is an extraordinary feat of engineering because not only do you have to make this big environment that people can live in, which, you know, is non-trivial to do on Earth, you have to do it in space.
It comprises millions of high-tech components. There are 16 pressurized modules with living quarters, sleeping bays, an observation deck, and 6 science labs, all connected via airtight tunnels. There's plenty of parking for visitors, including spots reserved for Russian Soyuz capsules, and the ISS's lifeboats, which are on permanent standby in case of emergency. Unlike any other structure, the ISS has to provide everything its astronauts need. If it fails, they die.
A human being can only survive for 3 weeks without food, 3 days without water, and 3 minutes without air.
For humanity to successfully venture well away from Earth, astronauts will need to be self-sufficient. If the ISS can solve the challenges, it will prove humans can truly live in space. But before anyone can take up residence, the engineers behind the ISS had to get it into space. And it weighs a colossal 460 tons, the same as about 300 cars.
It would be great if we could just build the International Space Station on the Earth and then just blast it into space.
You couldn't just fly the whole thing up there in one shot. You had to take a piece at a time and assemble it together like Lego.
The ISS began life as just 2 modules that had to be connected in space, one built by America and the other by Russia.
The first flight actually launched in November of 1998. Hadn't been that long since the end of communism in Russia, and here we were building a joint Russian-US space station. So just the political milestone that represented was pretty significant.
After the intense competition of the space race, it's suddenly all about collaboration. The orbiting Russian module is known as Zarya, which means sunrise. Next, the first American module, known as Unity, sets off inside the cargo bay of Space Shuttle Endeavour.
Liftoff of the Space Shuttle Endeavour.
Unity is now chasing Zarya through space at more than 17,000 miles per hour. 2 modules from 2 superpowers are about to dock.
first thing we have to do is to open up the payload bay doors.
Can you imagine how important it is for these two modules to mate?
Unfortunately, before both modules were launched, engineers spotted a problem.
Not all the pieces got to be integrated on the ground before they were launched.
Neither Zarya nor Unity were originally designed for the ISS. Their docking systems wouldn't fit together.
The Russian hatches are all round, and our hatches are all square.
I mean, this is fundamental to the International Space Station, and what you have are two things that don't mate.
And so, what do? Well, you make an Adapto-Lego block connector thing.
The L-shaped Lego thing they came up with is called the Pressurized Mating Adapter, or PMA. Not only does this accommodate the different shaped hatches, it also has a precision-engineered docking ring for grabbing hold of another module and perfectly aligning it. Vital if a reliable airlock is to be made. This is the moment of truth. Latches on the inside of the docking ring finally make the connection and pull the modules together.
Houston Endeavour, we have capture of Zarya.
The International Space Station is born.
It was amazing. I mean, here we are. We got airborne. We had Unity in the bay. And when we left a functioning space station ready for the next module to come up.
In the 20 years that follow, engineers from all around the world join the project, building their own space laboratories and bigger living quarters. But every one of the modules was constructed on Earth, and it takes a supreme international effort to launch them all successfully into space.
It took a long time to build Space Station. We have to fly everything up, we have to connect all the modules, put them together. So that took over 40 missions. Modules came from all over the world. We have the US modules from NASA, we have the Russian modules, we have the Japanese modules and the European module, you name it.
And it costs around $10,000 to send every pound of weight up here from Earth.
So right now, we're in the Japanese laboratory. It's one laboratory out of many here on the International Space Station. This is Columbus, the European module. It has science experiments all over. You could see it looks a little bit crowded. Here we are in the US laboratory. Again, this is a laboratory with science experiments on all of the walls here. So we're going into the Russian segment. Be ready. You don't need a passport either. And what's cool about this module, it is actually the very first piece of the space station that came up in 1998.
It's been occupied continuously ever since then. So if you think for 18 years, there has always been a human presence in space.
Today, the ISS is enormous. By far the largest space station ever created.
It's actually big enough if you have a good pair of binoculars, and when it's flying over, right overhead, you can actually see it. Normally you look at a satellite and it's just a little dot, but the ISS is big enough that you can actually see it as an extended object.
It's so vast, in fact, that it would dwarf Times Square. At an astonishing 357 by 240 feet, it has more living space than a 5-bedroom home. But the larger the International Space Station becomes, the larger a very obvious issue becomes, too. Air. In space, there is none.
It doesn't provide a life support system for us, air, oxygen. And so if we have a home in space, we need to provide all of that.
The average adult breathes close to 4,000 gallons of air per day. With a crew that can be up to 9, the ISS must supply a huge amount of it. And it's not coming from outside those windows. Cruising outside the Earth's atmosphere, the International Space Station has to provide everything the astronauts need to live. And breathable air is first on the list.
Their very survival really depends on the things that we provide them. And you're also having to deal with the fact that at any point in time, if one of your system fails, you have a very limited amount of time to either get something from Earth or to get back to Earth as quickly as you can.
In a crisis, an emergency supply of oxygen can be sent up by rocket.
3, 2, 1.
With technological advances, spacecraft can now rendezvous with the ISS in 6 hours, if everything goes as planned. But even when a cargo delivery is successful, there's a price to pay. The cost of each mission is colossal, almost $200 million.
It's expensive to bring a kilogram of anything up to the space station. And to spend all that money just to bring up water and oxygen would be an incredible waste.
The ISS needs to make its own air.
The oxygen on the ISS can come from a delivery from Earth, and then they're stored in tanks. But the ISS is also capable of generating oxygen on board.
On Earth, we take air for granted. In space, each astronaut must be supplied with 1.85 pounds of oxygen per day, 365 days a year, to avoid suffocating. In the very heart of the ISS is an unassuming machine about the size of a trash can. It's this that holds the secret to keeping astronauts alive. Incredibly, it generates oxygen from nothing more than water.
So what happens is you have some water, you feed some electricity through that water, and the electricity will split that water into hydrogen and oxygen.
The oxygen comes off as bubbles at the positive electrode, the hydrogen at the negative. But again, being in space turns something that's straightforward on Earth into a major engineering challenge. The bubbles of gas won't come out of the water.
In your high school chemistry lab, the gas just bubbles up to the surface because the gas is lighter than the water, and therefore it goes up. Gas is not lighter than liquid in space because gas doesn't have any weight and liquid doesn't have any weight. So you produce gas bubbles and they just sit there. And what we generally do is we centrifuge it. So you spin it all around, and the liquid, being denser, it doesn't weigh anymore, but it still has mass. So it's denser, and it goes to the outside, and you can then separate the liquid from the gas.
The hydrogen gets thrown away, gets pumped into space, and the oxygen is used for the ISS air supply.
There's enough capacity on board to generate 5 to 20 pounds of oxygen a day. More than enough for the crew. In the extreme environment of space, making air is just the first challenge. The ISS has to keep it, but it's under constant threat of a breach in its hull.
There is so much space junk up there now.
There's the potential for it to puncture the outer wall of Space Station.
I was taking pictures out one of the windows, and it was a nice clear window. I came back sometime later to take another picture, and there was a great big ding in the window about a 5/8 of an inch in diameter from a micrometeorite impact. And we had to take pictures, close-up pictures, send it down to the ground, and it had to be analyzed to see whether it was going to be a threat when we entered.
If you pop a hole in Space Station, the atmosphere is going to leave very, very quickly.
No atmosphere means no oxygen, and the consequences of that are obvious. So how does the ISS deal with the threat of colliding with meteorites? The International Space Station is the largest man-made object that's ever orbited the Earth. And it's racing around our planet at 5 miles a second. But on board, that's hard to appreciate.
How do we sense speed if you're in a car, for instance? You know, you have the road noise, you have the wind going by, you have billboards or trees going by your window. None of that exists in space. The only way you get a visceral sense of how fast I was going is, you know, you're going over the Pacific Ocean, and then 10 minutes later you fly over New York, and then 10 minutes after that you're flying over London.
If the ISS was orbiting closer to Earth, we'd all see how terrifying its speed is. It would cross the US from coast to coast in just 10 minutes, lapping the Earth more than 5,500 times a year.
But it's actually traveling at 26,000 kilometers per hour, or 17,500 miles per hour. So definitely be breaking the speed limit, right?
Speed on Earth can be incredibly dangerous, but in space, at the velocity the ISS hurdles, the consequences of a collision can be off the scale catastrophic.
Space debris is going by you at about 5 miles a second, so if there's a big piece of debris that happens to have your number on it, it's moving so fast you'd never see it.
March 23, 2012. Mission Control radios the crew.
And how about relative velocity? Any idea? Checking.
Something is heading straight for the space station.
The time of closest approach of this fragment of space debris is 11 minutes from now.
No one knows how big this object is.
Well, you do what you're trained to do, and even though you got woken up in the wee hours of the morning, you know what the reason is.
The crew must prepare the space station for impact.
Can you see it? Yeah. Yeah.
You go through and you close every single hatch on station, which takes about 45 minutes.
Yeah. And from which direction? Yeah, we don't know.
The hatches can withstand a sudden loss of pressure that would come from the hull being breached.
Coming up on the 6-minute mark.
If there is a puncture, any loss of air could lead to a serious emergency.
Coming up on the 3-minute mark until the time of closest approach.
The crew takes no chances. They head for the escape vehicles.
We floated into our Soyuz spacecraft with initial preparations for undocking if space station were to be hit.
About 1 minute from PCA.
And you just kind of hunker down and hope it doesn't hit you, and you just sit there and wait.
Looks like that's it.
Fortunately, this time it's a near miss. But the ISS cannot rely on luck.
The International Space Station is designed to work in the low Earth orbit, which is full of space debris.
A lot of space junk is human-made. You know, they are things that we have put up there, satellites largely.
NASA has identified more than 500,000 orbiting objects that could pose a risk to the integrity of the space station's hull.
Luckily, most of the stuff that's big enough to hurt us we can track. There are a few objects up there which are too small really to be tracked well, but they're big enough to do damage.
The ISS is constantly bombarded. Most of the debris is tiny, but even a half-inch fleck of paint could inflict the same damage as a motorcycle crashing at 60 miles an hour. To be a viable home, the ISS has to be able to take the hit without losing all its air.
The ISS basically has a bulletproof vest. So just like a bulletproof vest, which has different layers of Kevlar that can rip as a bullet enters it, the ISS has different layers in its outer skin.
The space station's skin is known as Whipple shield. The outer wall is made from a thin sheet of aluminum, less than 1/10 of an inch thick. Beyond that is a blanket of woven material and a further thin wall of aluminum. It seems too delicate to protect the ISS from a direct hit.
It turns out that a solid piece of metal does not offer as much protective power as if you cut that metal into very thin sheets, spread them out a little bit.
When there's an impact with a high-speed micrometeoroid, it hits the outer wall of the ISS and pulverizes. Some fragments pass through the first layer of aluminum, which disperses some of the energy. Then there are layers of Kevlar and Nextel, a ceramic fiber that's stronger than some metals. As the fragments hit this blanket, they break up even more and don't have enough energy to penetrate the hull.
It's kind of counterintuitive when you think about it, you know, that a whole bunch of sheets of aluminum foil could somehow give you more protection than putting them all together. But that's the way it is in space.
The Whipple shield has protected the space station from micrometeoroids for over 20 years. But it's ineffective against anything larger. If a large object on a potential collision course is identified, the only option is to move the whole ISS out of its way.
Space Command monitors most of the space debris that is out in orbit. They notify our mission control here at NASA. We look at that and we have a green zone, a yellow zone, a red zone.
Objects that fall within the red zone have a 1 in 10,000 chance of hitting the ISS. Too dangerous to ignore.
If we think that something is coming within the red zone, the space station can adjust its orbit and give itself a little boost to get out of the way.
Small thrusters change the ISS's trajectory, but using them is expensive.
Now these thrusters, you can think of them almost like tiny rockets, and those rockets are using propellant, and that propellant isn't infinite.
It all has to be sent up from Earth at a cost of $10,000 per pound of propellant. This brings engineers face to face with the greatest challenge of all: how to reduce the station's reliance on Earth. The ISS can't be self-sufficient if it relies on thrusters to move. But a clever trick hidden at its center means it doesn't have to. The International Space Station has a problem. It orbits the Earth every 90 minutes and has to be regularly reoriented. Using thrusters is one option, but that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station, usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the same relative orientation towards the Earth so that the cupola is looking down at the Earth. And in order to do that, of course, the space station is going to be rotating once every orbit around the Earth.
What the ISS needs is a way to move that doesn't use propellant.
The solution for keeping the ISS in the right altitude and also on track in direction is to use gyroscopes.
This is one of the ISS's most innovative secrets. At the center of the sprawling space lab, there's a quartet of small casings, each about the size of a small cupboard. They're known as control moment gyroscopes, or CMGs. But how can they move a beast the size of a football field?
They're really, really clever in that you can change the attitude of station without firing any thrusters.
The 4 CMGs are mounted on a truss near the very core of the ISS. Inside each casing is a flywheel, spinning at 6,600 RPM. The flywheels create a lot of angular momentum, and simply by changing the RPM, or tilting the plane they spin in, they transfer that momentum to the ISS, and the whole thing moves.
If I were sitting here in a chair and I had a gyroscope spinning around in this direction, and all of a sudden I put a brake on and slowed down the gyroscope, the chair would start to spin around. You know, I would slow the gyroscope around and then, woo, I would do a big spin because that angular momentum has to be conserved.
So these 4 control moment gyroscopes can move the whole of the International Space Station, and there is not one single drop of propellant used in order to make that movement.
But they do use electricity, as does just about every piece of equipment on board. To supply the ISS's total power requirement, a whopping 75 to 90 kilowatts, engineers cleverly exploit the ferocious power of the sun. The station generates all its electricity for free.
The solar panels on the space station are absolutely essential because they provide all of the power that the station needs.
The panels have to be enormous, which would have made them impossible to transport had NASA engineers not come up with a genius way to get them into space.
What's really impressive about the solar panels, not least their size, you know, around ½ an acre per array, but the fact that they are actually folded, and then once they're in space, they were able to be unfolded. Now that's an amazing thing to do in space.
Together, they can generate 120 kilowatts, ample for all the ISS's needs, and the equivalent of powering 40 homes.
In order to maximize the power you're getting, you have to keep this solar panels continually pointed at the sun, which means as the station is moving, the panels have to turn.
And so we have gimbals. If there's a solar panel, we can gimbal this direction, and then we can gimbal this direction.
One of the ISS's greatest engineering triumphs, it's been generating its own power for over 177,000 hours and counting. That enables round-the-clock air conditioning, fundamental to astronaut survival.
This cannot go down. It's not like a power cut in our homes where, you know, we can get a torch or light a candle or something. If this goes down, astronauts will die.
When the ISS enters the shadow behind the Earth, the temperature can drop to below anything ever experienced on our planet. Without the protective cocoon of the space station, the ferocious cold would kill astronauts in a matter of moments. Conversely, when in sunlight, the temperature can soar.
Temperature and managing temperature on the ISS is very important. If you imagine the extreme temperatures that you can get on the ISS if you're facing the sun or not, could be plus 250 degrees or minus 250 degrees.
So you have these huge temperature extremes simply because of being sunlit or being in the shade. And it's something that you have to keep in mind when you're doing your engineering.
Of these threats, overheating is the hardest to manage.
With lots of people and electronics inside a spacecraft, you tend to generate more heat than you know what to do with. And so the problem in general, at least in Earth orbit, is that you've got to get rid of heat.
If heat built up uncontrollably inside the ISS, it would become a deadly incinerator. So cooling the station is a crucial priority.
Standard ways of cooling that we're used to on Earth don't work. Convection does not work. Conduction does not work.
Conventional aircon would be ineffective. Scientists had to come up with a cooling system for radiating heat away from the ISS. It needs to be liquid-based, but there's a dilemma.
Ideally, what you'd like to be able to do is just put it through a water cooling system and then get rid of that excess heat. If they tried to get rid of that excess heat using water, the water would just freeze as soon as it went outside into space.
Water is not the solution. Curiously, gallons of a deadly poison is. Hidden inside the hull, there's an intricate network of pipes picking up the heat. But they do carry water. The secret is, the water goes through heat exchangers, where ammonia-carrying pipes take the heat outside the ISS. Huge radiators finally dissipate it into space. Ammonia is used because, unlike water, it doesn't freeze until minus 107 degrees Fahrenheit. It remains liquid and flows through the radiators, even when the ISS is behind the Earth.
Ammonia is used as a heat rejection system because it is one of the best thermodynamic fluids to use as a heat rejection fluid. Unfortunately, it's incredibly toxic and kills human beings on contact.
In May 2013, for reasons unknown, ammonia is spotted leaking out of one of the cooling pipes. There is no alternative but for astronauts to climb outside the ISS to fix it.
Fireflies coming off our space station.
The International Space Station has a network of vital cooling pipes that are filled with ammonia, a substance so toxic it can kill.
Now, there was a time in 2013 when Chris Hadfield and his crew spotted a leak from the ammonia pipes, and they had to react very, very quickly to stop that leak.
The leak appears near one of the solar panels. There's only one viable response to this critical emergency. Astronauts Chris Cassidy and Tom Marshburn must exit the ISS and investigate.
Sunlight, I am putting my visor down.
They discover ammonia spewing out of what they think is a pump.
Fireflies coming off our space station.
If they can't stop the flow, they might have to evacuate the space station.
You're going to monitor for an ammonia leak. If some reason a flowing leak is observed, immediately stop turning.
The pair attempt to replace the suspect pump. Hard work in cumbersome spacesuits. And they must avoid contact with the potential lethal ammonia.
Be careful not to put your hand inside that window, and also the seals on the FQDC are no touch.
No touch on the seals, don't penetrate the window, copy all.
5.5 grueling hours later, the astronauts return to the ISS unharmed.
That's affirmative. The ammonia valve is closed.
It was fortunate that the leak wasn't water, because along with oxygen, water is one of the precious commodities people cannot live without. It's so precious, in fact, that inventing equipment to recycle it was one of the space station engineers' highest priorities.
It's so important that we recycle as much of the water on the ISS as possible. And that includes things just like the water in the air.
The end goal is for the spacecraft to recycle 100% of their onboard water. That's far from straightforward, because much of it starts off inside the astronauts.
That water vapor comes from the individuals. As you breathe, you exercise, you sweat, and then it comes off of the surface. So that's the water vapor that gets out into the air, and we're constantly ventilating the air through the module.
Water vapor from the air is collected in a condenser. Every droplet is valuable. Nothing is wasted. Even urine is recycled.
Let's say you're up here on ISS and you need to go to the restroom. You want to come to this cabin, and the first thing you want to do is grab this piece of equipment and turn this rotary switch 90 degrees to the open position. What that does is it turns on a fan, which creates a suction effect in this hose, so that you can use this yellow element for your number one.
After an astronaut uses the unusual facility, water products flow to the life support rack, where filters get to work. The start of a sophisticated process.
So the way space station turns urine into water is that the urine goes into what we call the urine processing assembly.
There are a number of stages. The first is treating the urine to prevent buildup of bacteria or other dangerous microbes.
That urine that we collect from the crew, we have to add chemicals to it in order to process it. Raw urine in and of itself would be a problem because over time it becomes rancid, and that's definitely a bad situation on the space station. So that's why this is a dark fluid instead of what you would normally think of as urine.
Clearly, that is not drinkable. It needs to be distilled, where pure water is boiled off to leave the toxic waste products behind.
And then it goes through another cleaning process. There's lots of filters. And then some of the water is made available for drinking. And that's why we have the expression that the water recycling system is coffee to coffee. You can think about that.
The water that gets to the crew now is effectively cleaner than any water that we drink here on Earth. Even that nice bottled water that everybody likes so much, it's cleaner than that. So this is the end point in the process.
It tastes really good.
In water recycling, we are really trying to get to the point where we can recycle up to 90 or 95% of the water on the space station, which is really vital not only for going someplace like Mars, but also has consequences here on Earth.
Recreating the conditions that support life on Earth is one of the pillars of the ISS. But much of its equipment is still operated by Mission Control in Houston. The ISS will have to break free from that if we're ever going to conquer deep space.
We're going to have you go to the ticker shroud removal.
Okay, copy.
The International Space Station provides its own life support, but it's partly controlled from Earth.
Go off a bit. Off a bit. There it is. Yep, I caught it.
Okay, Swanee, what do you want for...
Our flight controllers on the ground can control the robot arm and move that from the ground.
That requires constant radio communication. A major challenge because radio waves can't penetrate the Earth, and the ISS is often behind it.
What a beautiful piece of hardware.
We can have significant loss of signal with the space station. We're talking on the order of maybe 12 to maybe 40 minutes, maybe a little bit longer.
In the early Apollo space missions, they tried to fix the problem with a fleet of jets that bounced radio signals between each other, ground bases, and space capsules. But it was expensive and unreliable. The ISS uses a more sophisticated system.
There are various assets that we're able to use to communicate with the International Space Station. So one are via satellites.
A network of high-orbit satellites relay radio data between the ISS and ground bases in several countries across the globe.
And Mission Control, we're looking at various video feeds. So we have the first board over here, we call it the 6-pack. And the International Space Station allows, at a minimum, 6 downlink video channels. And then we can be following the crew, what they're doing during their day.
Station Houston on Space to Ground 2, you have a go for Step 6, Ingressing Dragon.
Copy that.
The live links are so reliable and fast, there is now less than a second's delay when astronauts communicate with Earth.
Hi, Dad. Hi, Dad. How are you?
Hey, Rob. Hey, bud. How's it going?
Currently looking at what we call the world map. It would show that the International Space Station is currently about to start swinging north of Antarctica. Another cool feature about the world map that we keep in front of the control room is the fact when other missions go on launch, we'll also see those vehicles where they are relative to the International Space Station.
3, 2, 1. Engine ignition, liftoff of the Falcon 9 rocket.
The ISS may still be in our local space neighborhood with the luxury of near-instant communications. But it's also our first stepping stone to reaching other planets and beyond.
Science for today and for deep space exploration tomorrow.
Inside this rocket is an experimental new module known as BEAM.
The first human-rated expandable structure to be flown in space, now attached to the International Space Station.
After docking with the ISS, astronauts test its unique feature. It blows up like a balloon.
It's an inflatable module that's attached to the space station. It's kind of unique in that the fact it is inflatable.
Looks great, it looks pristine.
Pressurized air pumped into the extraordinary new module transforms it into a rigid structure.
One of the unique things about BEAM is that because it is collapsible, you don't need as large of a launch vehicle to carry it. Also potentially less weight because of less structure with it.
If successful, the ISS's brand new living quarters could lead to much bigger space structures. Ultimately, the plan is to house far more than the 220 people that have so far been to the space station.
We've been very privileged. We've seen our home planet from a very different perspective. First of all, it's incredibly beautiful. I mean, you look at the thin blue line that's our atmosphere, you look at the aurora, you look at thunderstorms, you look at the beautiful oceans. When you start looking a little closer, there are some troubling things. You basically see the impact that humans have had on our planet, and that can be pretty scary at times.
The long game for humanity could be to stop being a one-planet species. The ISS is the first step towards that future.
In the future, we're going to have hundreds, thousands, I hope it's 10,000 of people living, working in low Earth orbit.
Research on the ISS is heavily geared towards improving life for astronauts who will travel much further than ever before.
It's phenomenal. So it really is the world's greatest laboratory.
On space station, a lot of the experiments that they're doing are human-based experiments in order to learn more about the human body so that we can endure a 2.5-year mission to Mars and back.
From fitness to food production, the focus is on long-term self-sufficiency for astronauts.
And we are developing the Orion capsule here, which will be launching the first manned mission in 2022.
And liftoff at dawn, the dawn of Orion, and a new era of American space exploration.
Missions in the coming years are only possible because the International Space Station has solved so many of the problems that space presents.
The future for space is bright, and it's going to be exciting.
Everybody is excited and feel like as though in this development phase you can really make a difference.
The ISS is an incredible superstructure, a piece of Earth-like habitat floating above our planet, where every component has taken breathtaking engineering. It's now a vital springboard for deep space travel that generations to come might thank us for.